So we will come back to the biological pump later on. It's basically how biology moves the material, like the carbohydrates that are produced by photosynthesis, in the euphoric zone to the bottom, and how circulation moves CO2 and nutrients back. Okay, so there is a biological pump where biology is involved in moving material, and there is a solubility pump where the circulation, the physical circulation, is involved in moving material. We'll look at that a little bit later on. So let's first look at the productivity of the ocean in different regions. Again, you'll have to combine your knowledge of the circulation and light availability with the seasons, right? Remember, the sun is moving north to the Tropic of Cancer in the northern summer and back down to the Tropic of Capricorn in the northern winter. So light becomes available at different latitudes by different amounts at different times of the year. Tropics are almost always having enough light. So polar regions have almost 3 months of complete darkness. And there is summer sunlight, which begins to happen in the spring months as the sun crosses the equator after the spring equinox. The bloom, remember the thermal structure of the polar oceans, right? It's well mixed down to the bottom because there is no well-defined thermocline. So the nutrient concentration is always high. There is no nutrient profile. It's all high bottom to top to the bottom. As soon as light becomes available, then you can have production. And if there is production, then zooplankton begin to grow to eat it, but zooplankton take time to grow, so there is a phase lag between primary production and zooplankton that come along to eat it. So how does it look? You can see the diagram here. In the winter, you have very low productivity, so some seeds survive because of various mechanisms that we won't go into. And it's like grass that almost seems dead and gone during the dry season, but as soon as there is some rain, you get sprouts of grass everywhere, right? Similar things happen in the ocean. As soon as sun comes across and some light begins to be available and it's sufficient for primary production, diatoms are the main species that comprise the polar ocean productivity. There are reasons why specific species occupy specific niches. For example, I talked about photosynthetic bacteria. Those are called Prochlorococcus and Synechococcus. They have evolved to photosynthesize, and they compete at a certain depth because there are nutrients coming from above, light coming from below, and they have all evolved to live at certain depths and certain latitudes. So diatoms do well here, and they produce a huge bloom in the spring months. We are looking at the northern hemisphere, obviously. With the delay, you get a zooplankton bloom, which grazes down the phytoplankton, but you can see as the zooplankton biomass is beginning to increase with the delay, the phytoplankton biomass is beginning to drop, and the zooplankton biomass reaches its peak in summer months. By then, the phytoplankton has already been chowed down, grazed down. It's called grazing. Okay, this is like crows grazing. So zooplankton are grazing on the phytoplankton. So Arctic Ocean's Barents Sea has this typical kind of productivity. Polar ocean in the Antarctic is pretty amazing. I will show another slide later on krill and so on. What's happening in Antarctica? Remember what we learned before. We have the west wind drift, east wind drift. We have upwelling in the middle, dynamically forced. So you have the North Atlantic deep water being pulled up to the surface between the Antarctic bottom water and the Antarctic intermediate water. So remember, the North Atlantic deep water is being formed at the surface. Nutrients are being taken down with it as it sinks, and that nutrients are being brought up when this upwelling happens. So there are other issues that the Antarctica southern hemisphere has had. The issue of ozone hole. CFCs leaked into the atmosphere, stratosphere, and destroyed the ozone. ozone hole happened, which means UV, which is absorbed by the ozone and ozone formation, began to come down to the surface in larger quantities than normal. There is some evidence that they have affected the primary production. Okay, so this is the profile from sea level down to the bottom. The waters are basically isothermal and very cold, which means the nutrients are also very large, but the buoyancy of the diatoms helps them remain near the surface. So the primary production there, I will show the blue whale story a little bit later on, but essentially when the spring bloom happens in the Southern Ocean, remember it's a channel, the blue whales and some humpback whales time their arrival at the time that the primary production happens, because the krill, which are shown here, chow on the diatom bloom that happens. Remember, we mentioned krill is not neutrally buoyant. If it stops swimming, it'll sink, so it's always swimming, creating turbidity and very murky waters. But blue whale is huge, 3 buses long. It just opens its mouth and just filters million gallons of water, so the krill have no chance, right? So we'll look at the details as to why they go to eat the krill. Okay, why go all the way down from the North Pacific to the Southern Ocean to eat krill? So polar productivity looks like this, where it has a peak in the spring, and zooplankton peak follows the phytoplankton bloom, and that peaks in the summer. And the krill bloom happens obviously with a delay, and that's largest in the spring, early summer months. So blue whales and humpback whales go